Hello everyone, my name is Zixiang Zhang. Today I'm going to show you our recent work, learning-based fast depth encoding for 3D-HEVC via XGBoost. The co-authors are Li Yu, Jian Qian, and Honghui Wang. We all come from Huazhong University of Science and Technology. I will introduce our work from the following 5 aspects, so let's begin with the introduction. This video shows a popular visual special effect, bullet time, which needs a dense camera array system to achieve immersive watching experience. In order to get multi-view watching experience, a large number of cameras need to be erected throughout the scene seamlessly. As we can see, to save and transmit such massive data volume is a disaster, which is too expensive to affordable. This short video shows the free viewpoint live broadcast of the ice hockey project at the latest 2022 Beijing Winter Olympics. Different from the multi-view video system just mentioned, it uses a sparse camera array to realize 3D reconstruction of the scene with the aid of depth maps. This multi-view plus depth video format is relatively cheap to achieve free viewpoint watching experience. Because the MVD video contains texture and corresponding depth map videos of partial viewpoints and can synthesize virtual viewpoints of any intermediate position based on the BDBR technique. The 3D-HEVC is the latest MVD video coding standard, which has been finalized in February 2015 by DCC2022. This is the 3D-HEVC codec and transmission system architecture. At the encoding end, a set of texture video together with their depth map are encoded using 3D-HEVC encoder. At the decoder end, you can choose to decode the texture and the depth map of all the viewpoints and synthesize a group of intermediate viewpoints, or you can only decode the texture video of 2 or 1 viewpoints to watch. In other words, it's compatible with free viewpoint TV, stereo display, and conventional 2D display. To adapt to characteristics of the depth map, new coding tools have been introduced into 3D-HEVC, including depth modeling modes, depth interscape, motion parameter inheritance, etc. These new depth coding tools can obtain better coding efficiency, but bring high computational complexity for the 3D-HEVC codec. Here is the coding structure of 3D-HEVC. The left picture shows the access unit structure and the coding order. As we can see, the texture and corresponding depth map of all the viewpoints at the same time constitute an AU, which is encoded one by one. For each AU, the first encoded view is a base view, or independent view, and the other views called dependent views. The right picture shows the 3D-HEVC codec structure. Each component will be encoded using the HEVC-based encoder. Only the texture video of the independent view is encoded by the unmodified HEVC encoder. The other components are encoded using the modified HEVC encoder, which adds in the component prediction tools, as indicated by the right arrows. For example, the depth map of view 1 will take the coding results of the texture in view 1 and the depth map in view 0 as reference to perform prediction coding. Because the 3D-HEVC is an extension of the high-efficiency video coding standard, its coding process is basically consistent with HEVC. For 64x64 size CPU, it needs 85 attempts to determine the optimal partition by depth-first traversal. For each CU, it needs to traverse 11 prediction modes to determine the optimal prediction mode. Moreover, for depth map coding, there are more prediction modes need to be executed, such as depth interscape, segment-wise DC coding, depth modeling modes, etc. Among all of these prediction modes, the merge 2n times 2n and the scape mode are executed firstly. Therefore, we simply classify all PU modes into MSM and non-MSMs. This is a statistical analysis of the depth map coding results using original 3D-HEVC encoder. The left picture shows the distribution of CU size. It can be seen a large number of CUs are encoded with 64 × 64 size, and their proportion increases with the growth of QP. The right figure shows the ratio of MSM for different CU size. It can be seen more than half of CUs choose the MSM as the optimal PU mode, and their proportion increases with the CU size. So based on the unbalanced distribution of CU size and the PU modes of the depth map, if we can early determine CU partition and PU mode, we can obtain generous coding time saving. This is our proposed hierarchical classification architecture of ECP and EPM. For early CU partition determination, we call it ECP. 3 binary classifiers respectively used for different sizes of CU, including 64 × 64, 32 × 32, 16 × 16, to predict whether CU need to be split into sub-CUs. For early PU mode selection, we call it EPM. Different binary classifiers are inserted between the MSM and non-MSMs to predict whether MSM is the optimal mode for different PU sizes, including 64 × 64, 32 × 32, 16 × 16, 8 × 8. We separately tackle the base view and the dependent views because the interview correlation is unavailable for depth map coding in the base view. So totally 14 binary classifiers are used to achieve ECP and EPM. We choose XGBoost as our algorithm backbone. As a popular grading tree boosting method, it combines multiple weak classification and regression tree models to obtain an accurate overall result. The base linear is a simple cut model, whose max depth is set to 3 in our method. The XGBoost ensemble multiple weak cut models to build a strong prediction model and train the model in the gradient boosting way. The reason we choose XGBoost to accomplish the classification problem is it has relatively high accuracy, and it is convenient to be integrated into the encoder. Besides, it runs really fast. As for feature selection, we utilize multi-domain correlations, including spatiotemporal correlation, interview correlation, texture depth correlations. Based on these correlations, we choose a group of related CUs as shown in this picture. From potential useful as well as available features of related CUs and the current coding CU, a total of 76 features are extracted to train our models. The main features and their description are listed in this table. Some features listed in the table donate a group of features. For example, DT contains the depth level of the co-located CU in the first frame of the reference list 0 and list 1, in addition to the average depth level of the crisscross shape CUs. The FS contains the average value of merge flag of the special neighbor CUs, and the average value of skip flag of the special neighbor CUs, and the average value of SDC flag of the special neighbor CUs, and the average values of DNS flag of the special neighbor CUs. Besides, the interview domain features are unavailable for the base view, that we remove the interview features when training models for the base view. Here is a question: should we use all the extracted features or just part of them? Actually, it is a trade-off between the model accuracy and the complexity overhead. In our method, we choose all of them to fit into our model because the complexity overhead of feature extraction and the model execution is too small to ignore. Here is the experimental results. The first table shows the accuracy of XGBoost models. In general, The models of 64x64 size blocks have excellent accuracy, and the models for other sizes have relatively low accuracy. It is important to mention that the accuracy doesn't consistent with the coding performance degeneration. Specifically, for ECP, only the false negative samples result in RD performance degeneration because these CUs with the ground truth of split are predicted as non-split wrongly. Will the coding precise of false positive samples doesn't change. On the contrary, only the false positive samples for EPM result in RD performance degeneration. In this aspect, the percentage of performance degeneration for each model is no more than 16% and even less than 4% for 64x64 blocks. The table below shows the coding performance of our method and other related works. The BDBR of the synthesis views and the total encoding time saving are used for coding performance evaluation. It can be seen the proposed ECP algorithm can achieve 51.2% total encoding time saving with a 0.18% BDBR increase. For the overall ECP+EPM algorithm, even 60.8% total encoding time saving can be obtained with 0.59% BDBR increase, which greatly speeds up the depth encoding process in 3D-HEVC. This is the visualization coding result. It can be seen, for example, the 64x64 size blocks choose non-split in all methods, while the ground truth is split. Besides, less red dots can be seen in this figure, which means more CU chooses MSM at the optimal PU modes in all methods. The statistical result in this histogram is consistent with our observation. In general, the blocks with large size such as 64x64 and 32x32 in all methods are inclined to choose non-split and select MSM as the optimal PU mode, which brings more coding time saving by resulting in BDBR performance degeneration. In conclusion, this paper presented a learning-based fast algorithm for depth encoding in 3D-HEVC. The main contributions are as follows. Firstly, both the CU partition and PU mode selection are abstracted as binary classification problems. The hierarchical classification architecture of ECP+EPM was designed to accelerate depth encoding process. Secondly, considerable features from multi-domain related CUs and the current coding CU were extracted to construct the database for model training. A total of 14 specialized XGBoost models targeted for different block types were constructed offline. Finally, the XGBoost models were implemented into the HTM version 16.0, and the experimental results illustrate that the proposed algorithm can greatly accelerate the depth encoding process for 3D-HEVC with negligible coding performance degeneration. Thanks for listening.